Hello and good day, class. The topic for today will be about Introduction to Spectrophotometry. A few reminders before we start. Number one, please take down notes. A soft copy of this PowerPoint has been already uploaded in our MyLPU portal and OneDrive link. Ready your ball, pen, markers, and calculators if needed. Listen attentively, avoid unnecessary distractions, and give extra attention to information marked with a star. For our introduction, to spectrochemical methods, measurements po can be based on light and other forms of electromagnetic radiation, and this is widely used all throughout analytical chemistry or the laboratory in general. The interactions of radiation and matter are the subject of the science called spectroscopy. And under the term spectrochemical, we have the term spectro, which comes from the word spectrum, which means a band of colors like in the case of a rainbow, produced by separation of the components of light by their different degrees of refraction according to the different wavelengths. So in summary po, ang different colors po natin, they all have different wavelengths. So to give you an illustration of what does that mean, again, for example, here is your direct light. Upon striking a substance known as a monochromator po, this will separate the different wavelengths of light, having these different colors po of the rainbow. And if we will be looking on in the laboratory methods, it's more on the analytes po have their own unique wavelengths po that we will measure them with. So for example, your hydrogen is under this region, color red. Your sodium is under the orange region, and then magnesium, for example, is under the blue-green region. So in summary again, each of the analytes will have their own specific wavelength that we will need to input in our spectrophotometry machine. So going back, spectrometric techniques from the largest and most important single group of techniques used in analytical chemistry and will provide a wide range of quantitative and qualitative information. So aside from carry natin dito malaman kung positive or negative yung analyte dun sa sample, meron din po very important yung quantity niya. So aside from positive, negative, pwede din po yung mismong quantity kung gaano karami malalaman po natin using the spectrometric techniques. All spectrometric techniques depends on the emission or absorption of electromagnetic radiation, characteristics of certain energy changes within an atomic or molecular system. Going back nga po doon sa previous illustration natin kanina, this one, makikita nga po natin each analyte has their own unique wavelength. So the energy changes are associated with a complex series of discrete or quantized energy levels in which atoms and molecules are considered to exist. Lagi nga po yan na bago po natin ma-measure yung ating mga analytes, especially here in clinical chemistry, we should know at least what wavelength do we measure them. Kasi po tayo po, sila medtech po madalas kapag manual po yung machine or semi-automated yung machine, tayo po yung taga-input muna ng wavelength. Depende pa po yan doon sa instruction coming from the manufacturers of the reagents that we will be using. So next natin here, let's define energy, wavelength, and radiant energy spectrum. So under this, we have the term energy. This is transmitted via electromagnetic waves. Ito po yung waves na yan that are characterized by their frequency and their wavelength. Yung frequency po is yung dami po ng waves, ayan. And then yung wavelength naman po, it is defined as the distance between two successive peaks. And it is expressed in the terms of nanometers. So for example, here's the first peak. And here is the second one. The distance between the two is termed as, again, wavelength. Again po, the distance between two successive peaks or two successive frequency, it's termed as wavelength, and it is expressed, ang ating unit ng ating wavelength is nanometers. Okay, so again, that's nanometers. So here we have different types of electromagnetic radiation. So for example, we have radiation coming from radio and television. Aside from that, they're also coming from our mobile devices and cooking devices like our microwave. Kaya nga po siya tinawag na microwave kasi meron po talagang waves of energy doon po sa loob. That's why it causes the heating of food. And then aside from that, infrared coming from radiators. Visible light, kapag nasa visible light naman po ang ating spectrum, ito po yung nakikita ng mata natin, mga visible colors. Ultraviolet po, yeah, like coming from our sunlight, X-rays, and gamma rays. So these different kinds of electromagnetic radiation, most of this hindi po natin nakikita. Only those under the visible light can be seen with our eyes. Hindi naman po tayo nakakakita ng waves ng microwave. Di rin naman natin nakikita yung UV rays or X-ray, di ba? Yung mga waves coming from those materials. So again, only those under the visible light can be seen with our eyes. Okay, going back to the wavelengths, as I've mentioned po, each color of the spectrum has their own unique wavelength. For example po, the wavelength that is under 400 to 700 nanometers, those are under the visible spectrum. So lahat po na nakikita natin that's visible to the human eye, those are under 400 to 700 nanometer. For those that are under the UV region that's less than 400 nanometer, again, UV region less than 400. Infrared region that's more than 700 nanometers. Again, that's more than 700 nanometers. So again, let's just recall the different wavelengths. Visible po, 400 to 700. UV less than 400. More than 700 is the infrared region. And then the relationship between the wavelength and the energy is described by the Planck's formula. E is equals to H times V, wherein letter E is the energy of the photon in joules. H is the constant, and letter V is for the frequency. So again, the relationship between the wavelength and the energy is described by the Planck's formula shown here below. So again, energy is transmitted via electromagnetic waves that are characterized by their frequency and the wavelength. So again po, let's just recall now, wavelength po is the distance between two successive peaks. So kung ito po yung pinakamataas dun sa isa, here is the other one again, the distance po between the two is termed as a wavelength. And ano naman po ang frequency? Frequency po is the number of vibrations of wave motion per second. Yung literal po na wave, ayan, yung pattern po na yan, yung up, down, yan po ang frequency. Sabi po dito, when it comes to the relationship of frequency, wavelength, and energy, the lower the wave frequency, the longer the wavelength. Again, the lower the wave frequency, the longer the wavelength. So, let's illustrate here in the picture below. Paano po yung the lower the wave frequency, the longer the wavelength? Pag sinabi kasing low frequency, mababa lang po yung up-down. Ayan, kalma lang yung up-down natin. And this denotes po also low energy. So frequency and energy are directly proportional. But when it comes to the wavelength po, lower frequency, ayan, mas makonte yung vibrations natin, mas mahaba po yung wavelength or the distance between the two peaks. Again, low frequency, low energy will have a longer wavelength. In comparison, in the other term naman, short wavelength will have high frequency and high energy. As you can see in the illustration, madami po tayong wave. Yan, up, down, up, down, up, down, up, down. So that's a high frequency and also denoting a high energy. So again, frequency and energy are directly proportional. However, even though there is high frequency and high energy here, the wavelength is shorter. So high frequency, high energy will have a shorter wavelength. So that is the relationship between frequency, energy, and wavelength. Again, just to summarize, frequency and energy again are directly proportional while our wavelength po is indirectly proportional. The higher the frequency and energy, the shorter the wavelength. The lower the frequency and lower the energy, the longer the wavelength. So note, a slight error in wavelength adjustments can introduce a significant errors in absorbance readings. That's why nga po, bago po tayo gagamit ng spectrophotometer in each analyte measurement, we should know what's the specific wavelength for that particular analyte. Because of this po, even just a slight error can already have a significant error in absorbance readings po. So mamamali na po yung ating measurement. So, delving into the spectrophotometer. So, in the laboratory po, we are using different kinds of spectrophotometer from the semi-automated ones to the very automated or fully automated po na mga spectrophotometer. But commonly, most of them po, either the semi-automated or the fully automated machines po, they follow the same principle and they have their own parts of the spectrophotometer which they follow. So yan po, it can be like this, na maliliit lang, parang box lang. Pwede rin naman yung mga mukhang complicated na mga machines na mga high-end. So spectrophotometer, again, it involves measurement of the light transmitted by a solution. So ang pinaka-concern sa spectrophotometry is light to determine the concentration of the light-absorbing substances in the solution. Your spectrophotometer can be a single beam or a double beam spectrophotometer. And what's the difference of the two? For the single beam spectrophotometer, it is the simplest, again, pag single, simplest type. And then it is designed to make one measurement at a time at one specified wavelength. Again, pag single beam, isang measurement, one at a time. Kaya nga po siya single. The absorption maximum of the analyte must be known in advance when a single beam instrument is used, or kailangan alam na natin yung absorption niya before po natin siya gagamitin. So that's again the single beam. Again, single, simplest, one measurement at a time, one specified wavelength. So what's the difference naman po between a single beam and a double beam? Double beam spectrophotometer is an instrument po that splits the monochromatic light into two components. One beam will pass through the sample and then the other beam will pass through a reference solution or blank. Kung titingnan po natin dito sa ating single beam, as you can see, yung ilaw po natin, isa lang po yung dadaanan. This one lang. Comparing this with a double beam spectrophotometer, from here instead of dito lang po siya dadaan, meron pa po siyang isang pagdadaanan, which is the reference solution or the reference sample. So that's a double beam. Again, the monochromatic light coming from the monochromator will split into two. One po will pass through the sample or dun sa inyong specimen, and then another one po will pass to a reference solution or a blank. And then this additional beam will correct for variation in light source intensity. In this type of spectrophotometer, the absorbance of the sample can be recorded directly as the electrical output of the sample beam. In comparison with the single beam po, it should be known in advance pa. Dito po, pwede pong direct na measurement. So just to give a more illustration, single beam versus a double beam spectrophotometer. So again, single beam, diretso lang po, and then double beam po, there's a splitting of the light. Again, one will pass through the reference solution and then another in the sample or the specimen. And then under the double beam spectrophotometer, there are two types. The double beam in space, which has two photodetectors, and then a double beam in time, which has one photodetector. Again, double beam in space, dalawang photodetector. Double beam in time, isa lang. Katulad 'di ba kapag sa oras, isang beses lang lagi, one chance only. Hindi natin mauulit yung mga nagawa na natin before. So double beam in time, isang beses sa isang oras, something like that. So one photodetector use. So the difference po of this po, the double beam in time, since it only has one photodetector, there should be here some kind of chopper or mirror po, para po madedetect po yung dalawang light na magpapass through. In comparison kasi kay double beam in space, dalawa na yung photodetector. So to give a more in-depth idea and illustration of what does this look like, ito po yung illustration. So again, the double beam in space has two photodetectors. So again, here is the sample and here is the reference solution. One photodetector, then this is the second one. In comparison with the double beam in time, which only has one photodetector, as you can see, here is the sample solution and then the reference solution. And there are mirrors here and choppers so that both of the light po will be detected by one photodetector here. So again, double beam in space, dalawa. Double beam in time, isa lang po. So what are the 6 basic components of a single beam or double beam spectrophotometer? So although the two of them po, yung isa may chopper or mirror, but all of them has their own basic components which are the same, which is number 1 is the light source or the stable source of radiant energy, light source in summary. Second is a filter that isolates a specific region of the electromagnetic spectrum. a sample holder, a radiation detector, a signal processor, and a readout device. So let's watch this video for the spectrophotometer in the next slide. So this is how a spectrophotometer works. So this is the inside of a spectrophotometer machine. So as you can see here, there is a light source and here is the entrance slit. Here is the monochromator, and this monochromator will split the light, and here is the exit slit. From the exit slit, here is the sample. So here is the transmitted light, which will be detected by the photodetector. So yan, depende po kung anong wavelength yung kailangan po natin dun sa ating analyte. So that will be detected by the photodetector, and here is the readout device where you will see the measurement. And then we will dissect each part of this, our spectrophotometer, in the next slides. So again, here are the basic parts of the spectrophotometer that you have seen in the video. Number 1 again is a good light source. Second will be the entrance slit. Third is the monochromator. Fourth will be the exit slit. Fifth will be the cuvette. Sixth will be the photodetector, and number 7 will be the meter or readout device. Aside from knowing each part, let's make sure to memorize yung pagkakasunod-sunod po ng ating mga parts. Again, aside from knowing the different parts and their functions, again, please make sure to memorize the pagkakasunod-sunod of the parts of the spectrophotometer. In this way kasi, pag nakabisado niyo siya, mas makikita niyo po at mas ma-analyze niyo yung pinaka-function of each part. So again, here is the light source. So dyan po, ilaw, as in literal na ilaw po yan. And then, entrance slit, kung saan po papasok yung ilaw. Monochromator po. Monochromator po, again, will split monochromatic light. Yan. So, palalabasin niya po yung different colors of the rainbow. And here is the exit slit. Si exit slit naman po, padadaanin niya lang yung isang kailangang ilaw lang. Kasi hindi po naman yan lahat is needed. Again, each analyte po will have their own unique wavelength that we will be measuring them with. So for example, nandun kayo sa green region ng spectrum, yun lang ang kailangan, yun lang po ang padadaanin ng exit slit. And then here is the cuvette. The cuvette po is yung lalagyan po ng sample. This is where you will place your sample or the specimen like the serum, blood. And then next part will be the photodetector. The photodetector is the one who will detect the light coming from the cuvette. So the photodetector po will detect how much light is transmitted or absorbed by our cuvette. And then from there, the photodetector po, magkakaroon po siya ng translation from light into photoelectric energy so that we can measure and see the measurement of the concentration of the analyte in the readout device. So ito na po yung screen na nakikita nyo sa labas. Commonly, from the light source up until the photodetector, most of them po are inside the machine, and the readout device is the one po na makikita nyo sa labas ng machine kung saan nyo po mababasa yung resulta natin. So those are the basic parts of our spectrophotometer. To continue the discussion, here is the different parts of the spectrophotometer. We will start with the light source. So here it is in our parts of the spectrophotometer. Your light or radiant source will provide polychromatic light and must generate sufficient radiant energy or power to measure the analyte of interest. An intense beam of light is directed through the monochromator and the sample. So, yung ilaw po na mag-i-strike sa monochromator tsaka doon sa cuvette natin, manggaling po yan lahat sa light source. And to give accurate absorbance measurement throughout its absorbance range, its response to change in light intensity must be linear. Again, dito po magsisimula ang lahat sa magandang light or radiant source. So we have two types of light source, the continuum and the line source. Continuum source emits radiation that changes in intensity. Kaya nga continuing because it can change depending on the intensity. widely used in the laboratory because of that reason. Example of this, the most commonly used light source, which is the tungsten light bulb. Again po, palagyan ng star. The tungsten light bulb is the most commonly used light source in the visible and near-infrared region. Again po ha, ang visible po natin na region, that's 400 to 700 nanometer. Yung ating infrared region po is nasa more than 700. So again, for visible and near-infrared only, that is for the tungsten light bulb. Next po natin is the deuterium lamp. And deuterium lamp po will be good for the UV region. Kasi nga, di ba, each of the region, UV, visible, and infrared will have different wavelengths po. So, if you want na nasa UV na, since the tungsten light bulb is only under visible and near infrared, wala po siya sa UV, we can use an alternative like the deuterium lamp. And aside from that, we also have the xenon discharge lamp, which will produce a continuous source of radiation which will cover both UV and the visible range. So yan po ha, continuing po changes in intensity. Another type po will be the line source. Line source emits limited radiation and wavelength. Limited only. Letter L limited. Yung isa, letter C, continuum. Letter C, changes in intensity. And then a good example of our line source will be the mercury and sodium vapor lamps. And then aside from that, by the way, mercury and sodium vapor can be used in the UV and visible region. We also have your hollow cathode lamp. Another recall question, palagyan po ng star, your hollow cathode lamp is the light source for AAS or the atomic absorption spectrophotometry. Again po, your hollow cathode lamp is the light source that is preferred for AAS or the atomic absorption spectrophotometry. Line sources that emits a few discrete lines find when used in atomic absorption, molecular, and fluorescence spectroscopy. And then under also line source, we have light amplification by stimulated emission of radiation, commonly known guys as laser. Ayan, si laser pala, meron pala siyang ibig sabihin. Again, that's light amplification by stimulated emission of radiation. That is under line source. So factors for choosing a light source. Why is it ba pinapalitan natin? Again, the most commonly used will be the tungsten light bulb. But why is it pa kailangan pa ng iba? Number one po can be due to the range and also the spectral distribution within the range. Kasi what if, di ba, si tungsten, kaya niya lang po visible and near infrared. What if ang kailangan talaga is UV or yung matataas na infrared region? And then that can be a factor for choosing a light source. Aside from that, source of radiant production and stability of the radiant energy as well as the temperature needed for the measurement. So here are good alternatives to the tungsten light bulb as also mentioned earlier. The mercury arc for the visible and UV. And ito na-mention din kanina, the deuterium lamp at 165 nanometer, also good for UV region. And then hydrogen lamp and xenon lamp are also good for the UV. For the infrared region, we have the MERS glower and glow bar coming from silicon carbide. Okay, next part coming from the light source will be the entrance slit. So from the entrance slit, here is it in the parts of the spectrophotometer. That's the second part. This will minimize unwanted or stray light. Di ba kasi class, pag ang ilaw binuksan natin, nag-i-spread po yung light. Hindi po siya like one direction lang. So with that in mind po, pwede tayo magkaroon ng mga stray light or those stray light po refers to any wavelengths outside the band transmitted by the monochromator. It does not originate from the polychromatic light source and this can cause absorbance errors po. So stray light limits the maximum absorbance that a spectrophotometer can achieve. So that is a source of error. And stray light is the most common cause of loss of linearity at high analyte concentration. So mamamali po yung ating measurement. At dyan po papasok ang entrance slit or yung trabaho or function ni entrance slit. This will minimize that unwanted or stray light and prevents the entrance of scattered light into the monochromator system. So kumbaga para siyang guard na kapag hindi ka pwede, hindi ka papapasukin. So yan po ang entrance slit. Third part po natin will be our monochromator. So dito po yan again, light source, entrance slit, monochromator. Ayan. Monochromator po will now isolate specific wavelengths of light. Siya po yung magpapalabas ng different colors of the rainbow. Di ba nga sabi nga natin, each of the color po will have different wavelength. So yung magpapalabas po ng iba't ibang kulay na yan ay si monochromator. So here we have the different kinds of monochromators. We have your prisms. These are wedge-shaped pieces of glass, quartz, or sodium chloride. So para po siyang something like a diamond. Di ba ang diamond pag tinapat sa sunlight or sa ilaw, naglalabas siya ng rainbow. Ganon din po ang ginagawa ng mga prisms. This can be rotated, allowing only the desired wavelength to pass through an exit slit. A narrow light focus on a prism is refracted as it enters the more dense glass. So here is again a prism. Next po natin are the diffraction gratings. Diffraction gratings is the most commonly used monochromator. Again, diffraction grating is the most commonly used monochromator. Ayan. Better resolution than prism, and these are made by cutting grooves or parallel grooves or slits into an aluminized surface of a flat piece of ground, and the wavelengths are bent as they pass the sharp corner. So, yung mga colors natin, pag tumama siya dun sa parang step ladder, maka po kasi siyang hagdanan, di ba? So, pag tumama po yung ating ilaw dyan, magpapalabas po yung each step na yan ng different colors po, thus separating the different wavelengths of light. Katulad po nga nung main function nung sinabi sa monochromator. Again, the most commonly used po, diffraction grating, mukha po siyang hagdanan, parallel grooves, or cutting grooves. We also have filters. Filters are considered as the simple, least expensive, not precise though, but still useful. And then we also have your holographic grating. So if we will be comparing the diffraction grating with the holographic grating, your diffraction grating po mukha po siyang stepladder, while your holographic grating is mukha lang po siyang block. Isang block po, wala po siyang steps, but still it is able to isolate the specific wavelengths of light. Okay, next part po natin will be your exit slit. So again, let's just recall the different parts. Light source, entrance slit, monochromator, exit slit. For the exit slit po, this will control the width of the light beam or the band pass. Band pass is the total range of wavelengths transmitted, allows only a narrow fraction of the spectrum to reach the sample cuvette. Yun nga po, as mentioned earlier, exit slit po, padadaanin niya lang yung kailangan lang pong ilaw. Kung kunwari green lang ang kailangan, yun lang padadaanin niya. For accurate absorbance measurement, this will require a band pass that's less than 1/5 of the natural band pass of the spectrophotometer. The degree of wavelength isolation is a function of the type of device used and the width of the entrance and exit slit. Spectral purity of the spectrophotometer is reflected by the band pass. That is, the narrower the band pass, the greater the resolution. So that is your exit slit. Again, this will control the width of the light beam or the band pass, allowing only a narrow fraction of the spectrum. Kung ano lang kailangang ilaw, yun lang ang padadaanin ng exit slit. Fifth part po natin will be your cuvette. So again, let's recall, light source, then ilaw, dadaan sa entrance slit, monochromator, papalabasin yung rainbow, different colors po. Si exit slit, mamimili ng isa. And then yung ilaw na pinili niya po, tatama po yan ngayon sa cuvette natin, also known as your absorption cell, analytical cell, and sample cell. This will hold a solution or sample whose concentration is to be measured. Basically, siya po yung lalagyan ng specimen. Mukha lang po itong maliit na test tube po. As in, maliit lang siya and very sensitive na test tube. That's a cuvette. So different kinds of cuvettes includes the following: the aluminous silica glass, which is the most commonly used and can be used under 350 to 2000 nanometers. We also have your quartz and plastic, used for measurement of solution or sample requiring visible and UV region only. Borosilicate glass and soft glass. Ayan, dito nga po sa picture, ganyan lang po kaliit commonly ang ating mga cuvette. So it's like a test tube again, but more smaller. Smaller siya and much more sensitive. So notes to remember regarding cuvettes. Number 1, cuvettes with scratches po on their optical surface scatters light and should be discarded. Imagine class, a test tube na maraming scratch. Pag po tinamaan natin ng ilaw yan, magkakaroon po ng interferences yung mga scratches. That's why cuvettes with scratches po should not be used and should be discarded already. Very sensitive guys ang ating mga cuvettes. Commonly po, recommended sa amin before nung ako po yung nag-work sa lab, nung manufacturer namin, tubig lang po yung panghugas sa kanya. Bawal po yung may mga bleach. And also, of course, test tube brush kasi it can introduce scratches po dun sa cuvette na. Next here, silica cuvettes transmits light effectively at wavelengths of greater than or equals to 220 nanometer. Alkaline solution should not be left standing in cuvettes for prolonged periods of time because alkali slowly dissolves glass produces the etching. This path length of cuvettes, yung distance po, ito, yung length niya, it is approximately 1 cm or 10 mm. Kindly take note of that. The path length of the cuvette will have a effect or will have an effect po dun sa final concentration ng ating analyte. Although much smaller path lengths are used in automated system or mas maliit po na mga cuvettes ang kinakailangan. And to increase sensitivity, some cuvettes are designed to have a path length up to 10 centimeters pa, increasing the absorbance for a given solution by a factor of 10. Next part here, we have your photodetector. So let's just recall, light source, entrance slit, monochromator, exit slit, cuvette, and then the last nga po again is your photodetector. This detects and converts transmitted light into photoelectric energy, and it detects the amount of light that passes through the sample in the cuvette po, then it can measure the final concentration. Again, it will convert the transmitted light into photoelectric energy that we can see in the readout device as the final measurement. So here we have the different kinds of photodetectors. We have your barrier layer cell, photocell or the photovoltaic cell. This is the simplest detector, least expensive but temperature sensitive. It is used in filter photometers with a wide band pass. It is a basic phototransducer that is used for detecting and measuring radiation in the visible region. It is composed of selenium, ito po tingin sa screen, on a plate of iron covered with a transparent layer of silver. Will require an external voltage source but utilize internal electron transfer for current production with a low internal resistance. This typically has a maximum sensitivity at around 550 nanometer and the response falls off to about 10% of the maximum at 350 to 750 nanometer. Next kind of photodetector, we have the phototube. Ito po yun. Mukha po siyang light ng Christmas lights. Para po siyang bulb ng Christmas lights. Ganun po siya kaliit. It contains a cathode and anode and closed in a glass case. Diba? Para talaga siyang Christmas lights. It has a photosensitive material that gives off electron when light energy strikes it and will require an external voltage for operation. And then next here, the most commonly used photodetector, we have your photomultiplier tube or the PMT. Measures visible and UV regions as well and has an excellent sensitivity and has a rapid response, able to detect even very low levels of light. The response of the PMT begins when an incoming photon strikes a photocathode. These tubes are limited to measuring low power radiation because intense light causes irreversible damage to the photoelectric surface. It should never be also exposed to room light because it will burn out. So again, that's the most commonly used photodetector, which is your PMT or the photomultiplier tube. And then we also have your photodiode. It is not as sensitive as PMT but with excellent linearity. It measures the light at a multitude of wavelengths and detects less amounts of light. It has a lower dynamic range and a higher noise compared to the PMT and most useful as a simultaneous multi-channel detector because of it can detect multitude of wavelengths. So kaya niya po yung different wavelengths natin. So that's a photodiode. And then the last part of our spectrophotometer will be the readout device. So again, this is the last part. This will display the output of the detection system. Dito nyo po mababasa yung final measurement. Good example are the galvanometer, ammeter. So yun po yung parang katulad sa calculators. LED displays are already also available. Minsan pa may mga touchscreen pa. So let's just recall the different parts of the spectrophotometer in general. Again, it will start again on a good light source. Most commonly used is the tungsten light bulb. We also have the entrance slit. monochromator, which will isolate specific or different wavelengths of light, exit slit, cuvette, photodetector, and readout device.